In this problem, we're given the differential equation governing a circuit. We don't know what the circuit itself looks like, except it has an input I of t and an output V of t. We want to find the frequency response of the circuit. That means I'm finding the steady state sinusoidal response as a function of frequency. So I'm going to do this problem exactly the way I used to do it when I knew a single frequency that was input to the system. Converting to the frequency domain, I'm going to claim that the input I of t is going to be a function, which is a phasor, I, but it's now a function of omega times e to the j omega t. Since I'm looking for a frequency response, the implication is that I want a steady state sinusoidal response. So the function v of t is going to have the same form as I of t. It'll be a voltage phasor, which also depends on the frequency of the input, times e to the j omega t. So I can plug this in for this. I can plug this in for this. I need dv by dt over here. So dv by dt is equal to j omega v as a function of frequency, e to the j omega t. And I can plug that in there. So substituting 100 times j omega, phasor v as a function of omega, e to the j omega t, plus 2 times this v here, v as a function of omega, e to the j omega t, is equal to 100 times I of t, which is I as a function of omega, e to the j omega t. The same thing happens that always happens in the frequency domain. The e to the j omega t's cancel out, and I'm left with something that is no longer a function of time. So doing a little bit of math, v of j omega times 100 j omega plus 2 is equal to 100 I as a function of frequency. The frequency response, h of j omega, is the ratio of the output phasor as a function of frequency to the input phasor as a function of frequency. So this, dividing both sides by I of j omega and dividing both sides also by this term, is 100 over 2 plus j 100 omega. And there's our answer.